So our next topic, ultrasonic testing. A little bat image here. They like to use ultrasound. But for us, ultrasound is, we're going to be using sound to test our material. And we're going to be using sound that is high frequency. So that's where the ultrasound part comes from. So sound is only possible if you have a medium for it to transmit through. So it's a vibration that travels through the air or another medium, another material. And so our medium, our material, is going to be the object typically that we're going to be inspecting. Human hearing, what we can hear now, runs in the range from about 20 hertz or 20 cycles per second up to about 20 kilohertz, 20,000 cycles per second. That is when you are young. As you get older, this top range, the 20,000 hertz, tends to drop off. In all likelihood, you can hear higher pitched sounds than I can hear at this point. And as you get older, that'll drop off a little bit. But there's not a lot, and we're not doing anything with ultrasound testing where we have to be able to hear it. We're going to use instruments to do that. But what ultrasonic essentially means is we're going to be operating most of the time above that 20,000 hertz range. So ultrasonic testing, that high frequency, we're typically running somewhere in the 100 kilohertz, 100,000 hertz, to 25 megahertz range, or 25 million hertz, so cycles per second. And what we do is we induce a sound wave into a material. We have a device that produces that ultrasound, and it is induced or introduced into the material. It propagates or moves through that material. And as it moves through the material, any changes in the material density, form, shape are going to affect how that sound wave moves through the material. And so things like a crack, a discontinuity, or a disbond will cause reflections or deflections or changes in the sound energy in some way different than what we would expect if the sound was traveling through a part that wasn't damaged or didn't have that crack or defect or disbond. And so as it passes through the part, then we're going to listen, the device, the tester is going to listen for what the result is, what happens to that sound on the other end, or when it reflects back. So one way is the energy can be passed through a part, and we see what the energy looks like when it comes out the other side. Or we can send a sound wave into an energy, and when it hits something, it's going to reflect off of that and come back towards the original direction it is. So there's two ways we can do testing, and you can detect things, what's being reflected or what's passing through a material, or you can also be detecting what's not being reflected or what's not passing through a material. You know, those different, the different things that occur like that can tell us different things about what's going on inside of that material. Those two different ways are typically called pulse echo, where we send a pulse in and receive the echo, or what's called through transmission, is where we put sound in one side and we listen for it at the other end. So we'll look at some examples of that as we get a little further into this. Ultrasonic testing has some distinct advantages over some of the other methods we talked about. The biggest one is that it works on most materials, where some of the other methods we've talked about, eddy current testing, for instance, where the material has to be electrically conductive, typically a metal, right? Magnetic particle inspection, we have to have ferromagnetic parts. So not just electrically conductive, but can be magnetized as well. This can be done on materials that are not necessarily metal. So it's a very common method to use on things like composites, where you're dealing with fiberglass, glass fiber reinforced plastic, or carbon fiber, CFRP, carbon fiber reinforced plastic, carbon fiber, or other types of composite materials like this. But it can be used on metal parts as well. It often is used on metallic parts, and in some cases can be used as an alternative to like eddy current testing or something like that. We can do very deep penetration. We can actually see kind of through parts in a way. So pretty much all the other methods we've talked about up to this point, right? Liquid penetrant, magnetic particle, eddy current testing have all been primarily for finding surface flaws. ultrasonic testing can find subsurface flaws. It can be used for surface flaws as well. So it's versatile in that respect. You only need limited access to the part because you can send the sound through it. There are cases where they use this often on like buried oil pipelines, where you just need access to one part of the pipe. They can send a sound wave that travels down the entire length of the pipe underground and reflects back to that point. And if you get cracks in any part of that pipe, you can kind of judge about where they are. So it can go, and you're talking, it can go several miles underground in that case. So you don't need access to the entire area that you're looking for. I mentioned the subsurface flaw part of it. We can use it to do things like thickness measurement. And it has the ability, your newer testers can actually do 3D visualization, just like we saw the real high-end eddy current testers that can do what's called a D-scan. You can do D-scan ultrasonic testing as well that can give you 3D representations of the object that you're inspecting. Some limits, though, is it's not as good at detecting surface flaws as some other things. Small cracks in the surface typically are better found using something like eddy current or liquid penetrant in many regards. We'll look at how the sound waves propagate or move through the material. And depending on which way we send the sound waves through the material, there are applications where this will work better or less well for finding those kinds of surface flaws. Things like irregular geometry and rough surface are hard to inspect. We have to be able to get that sound into and out of our part. And so if you have irregular parts like that, it can make that difficult. You also will get sound reflections and changes in sound due to the geometry of the part. So a particularly complex part, you'll get a very complex return sound wave that may be sometimes hard to interpret. Is this a non-relevant indication because of the geometry of the part, or is it a relevant flaw indication because of that? So composites, though this can be used on composites, they aren't always the easiest to inspect. Composites the nature of composites is that they're not a homogeneous material, right? You typically have some kind of a reinforcing matrix in there, a fiberglass, the glass fibers, the carbon fibers, even metallic honeycomb and that kind of thing. And then you have your different plastics, your epoxies that make up the plastic component of it. And every time that material changes, as that sound wave's passing through the material, as it goes from a glass fiber into the plastic epoxy, back into a glass fiber, back into the plastic epoxy, that's going to introduce some kind of a return signal or some kind of a attenuation, a blockage of that signal traveling through the part. And so this is heavily used for composites, but it has to be carefully designed to work with the composite that you're inspecting. And the inspector has to be trained to inspect the composite that's being tested in order to understand and be able to interpret the results of that inspection. The equipment is comparatively expensive, especially when you compare it to something like dye penetrant, where you just need a few spray cans to do very basic dye penetrant. This is electrical equipment, it's precision equipment, it has to be calibrated, and so there is an expense there. And then the skill level, the inspector, this requires a greater degree of training and experience, hands-on time with the equipment than some of these other methods do to get really good at it and to be able to do it consistently. Before we get into how the testing works, we got to understand how sound works. And so the biggest characteristic of sound is that it travels in waves. And we get something called compression and rarefaction. And what's shown here with this spring is there's an area of compression to the right of the hand and an area of rarefaction to the left. So compression is where the atoms in a material are closer together versus the areas where they're spread further apart. Okay? So it travels in waves where those atoms move closer together and further apart as they move through the material. And we're going to look at things like the frequency, the wavelength, how fast the sound waves travel, the velocity, and the amplitude, how big of a change in position of the atoms do we see. So just a few kind of reminders about when we're looking at anything that travels in a wave. There are going to be different things that describe that wave, the properties of that wave. So frequency is the number of cycles per second. How many times does that wave go up and down or back and forth in 1 second? And we're looking at ultrasonic, so it's above that 20,000 hertz range. Again, 100,000 hertz to 25 megahertz, 100 kilohertz, 25 megahertz. And it's known as cycles per second. Okay, gives us a hertz. 1 cycle per second is 1 hertz. The wavelength then is how far apart the same point is on two peaks or two valleys or two identical points on that wave. So the wavelength shown in the bottom here is you can do it from one peak to peak. It can also be from one valley to one valley. Okay, that's going to be the same. It can also be from one midpoint to one midpoint, but if you're looking at midpoints, be careful. You need to be, here, if we do the midpoint on the part of the wave that's going up, we need to go to the midpoint of the part of the wave going up on the next cycle as well. Okay, just be careful if you're doing midpoint, you don't go from the midpoint of the part of the wave going up to the midpoint of the part of the wave going down. That's not going to give you an accurate wavelength. So typically high frequency is going to have a shorter wavelength. Low frequency is going to have a longer wavelength. They're inversely related to one another. Okay. Waves then travel there's two primary ways we're going to see waves travel. There's actually more than two, but there's two primary ways we're going to look at wave travel when we're doing ultrasound. And then we'll get into a third one in a minute. But waves can travel longitudinally or transversely. You can look at them in two different ways. And so a transverse wave is what most people probably think of as a wave. This is the up and down wave that you see on the bottom half of the screen. Okay. A longitudinal wave is motion within a material that's parallel to the direction of travel. And that's demonstrated by the compression and rarefaction that's taking place. So I've got an example of these. So I'm going to pause things real quick, and I'm going to ask those of you. So those are two types of waves and kind of an illustration of it. Here's another kind of picture of them. And you can see this shows what different wavelengths look like on our wave. So if we have a longitudinal wave, the wavelength is from a compression point to a compression point, or from the point of greatest rarefaction to the point of greatest rarefaction. If we have our shear wave, you can see in this case, they're showing the wavelength is from a peak to a peak. Again, kind of what most people are seeing. So most people are probably most familiar with a shear wave, or also known as a transverse wave. For most of what we're going to do in ultrasound, in fact, the labs that you're going to be doing, you're primarily going to be working with longitudinal waves. We're going to send a sound pulse into a material and look at how long it takes to come back. We're not going to work with the transverse waves as much as we will with longitudinal waves. It doesn't want to click. So just right out of that, in a longitudinal wave, we have particle motion that is parallel to the direction of the wavefront. So it's moving. It was when I ran that pulse in the slinky, the movement is kind of, in my case, left to right, right? It's moving to the left a little bit and back to the right a little bit as that wave moves through our slinky or through the air. So it's moving parallel with that direction of travel. And that's what the audible sound waves are that we're using. That's primarily what we're getting. The very edges of the wave exhibit the transverse or shear wave effect. But for the most part, what's coming out of my mouth, what's hitting your eardrum, what's traveling through there, what we're going to be putting into the part when we do ultrasonic testing, that's going to be a longitudinal wavefront. They're the fastest, so they actually travel a little bit faster through the material because the material doesn't have to move very far. The individual atoms move less than they do in a shear wave or in a surface wave we'll look at in a minute. And they can be generated in all different kinds of materials. So materials can include solid, liquid, gas, and they can transfer between different materials. So you can have a wave that, how many of you have been underwater in a pool and you can still hear other people yelling above the water surface, right? Do you swim? So people are yelling above the surface. You can't hear it very well. You can't make out what they're saying because your ears are not adapted to having water hitting the eardrum. Your ears are adapted to air. But you have noise traveling through the air. It gets to the surface of the water. It travels through the water. And then that water, there might be some air in your, trapped in your ear. That water might be up against your eardrum. And it causes those vibrations to go into your ear. So they can move through different things. So we can actually we can perform ultrasonic tests in some cases without ever touching the part. We can submerge a part in water or liquid or oil, and we can send the sound wave through the oil and eventually into the part without ever touching it. Or there's even, I've got a video where they have an ultrasonic tester. It goes around the part and it shoots a jet of water onto the surface of the part. And it's using that jet of water to transfer sound from the transducer through the moving jet of water into the part, and then the sound that's reflecting back through the part or traveling through the part is traveling through another jet of water into a pickup transducer. It doesn't actually touch the part anywhere, but it's a pretty cool thing, and it's moving water. There's going to be a lot of extraneous noise from that water moving around, but we can filter that out. When we have that shear wave, that's where the particle motion is perpendicular. So the wave is moving, when I did the example here from left to right, you saw that when I did a transverse or a shear wave, that slinky was kind of moving this direction, was moving front to back, away from me and towards me here. And so that's where that perpendicular motion comes into play. So the wave's still traveling left to right along this front table, but the movement of the slinky is perpendicular to it. The movement of the shear wave was perpendicular to it. They're not quite as fast. There's a larger distance. The individual atoms, or like the individual rings of the slinky, has to move, and so they don't travel as quickly. Okay, and then at the same frequency, at a given frequency. These are used sometimes in what's called angle beam testing, and we're not going to do angle beam testing. We have equipment that can do it. If you want to try it, it's not part of the lab, but later on, if you want to try it, we do have some angle beam testers. We have a tester that is capable of doing it, but we're not going to do it as part of our lab. And it's often used for a case where you can't have direct access to a part. The example that's probably most common in training is if I have two pieces of metal plate that are welded together. They got a weld bead like that, and they're kind of welded together here, right? If I want to check this weld, I can't put a probe directly on it because it's not a flat surface. So an angle beam tester is set up. I could put it off to the side, and it's going to send a sound beam in like this. And we can check a weld, for instance, without being able to put a probe directly on top of a rough surface or a not flat surface. So that's the kind of the most common example of like how does angle beam testing work. So the third type, this is another one used more in a specialty situation, is what's called a surface wave. And this is the particles move in a elliptic or oscillating motion along the surface of the material. And I actually accidentally did it with the slinky there. It's a combination of a shear wave and a transverse wave. Okay, sorry, a shear wave, which is a transverse wave, and a longitudinal wave. So it was kind of where I did that first attempt at a longitudinal wave, and it kind of kicked out to the side. So I'm going to go ahead and show that real quick on purpose this time. So what we can do with a surface wave is we can send it along the surface of the part in order to check for surface cracks. And that's what they do on things like those buried pipelines. So it looks something like this. So if we look at the one yellow dot here in the surface wave example, and you kind of trace its path, you can see it makes kind of a circle or oval shape. So it's moving, this wave here is moving from left to right, right? So that position of that one atom is moving both perpendicular and parallel to the direction of travel. This looks like what we just did. Okay. So we talked about what compression and rarefaction are. I've got just a little clip video there. That's a file. I don't think it'll work in your slides that I post. But it's showing the same thing that we saw with the slinky. It's showing this what's happening in this longitudinal wave. So compression is the increase of density as that longitudinal wave moves through our material, where the atoms are moving closer together. That's going to be a localized area where you have an increase in density, right? Atoms closer together makes the material more dense. And the areas where they move further apart, the areas of rarefaction, you're going to have a decrease in density. Now this is at the atomic level, right? We're dealing with these vibrations moving through a material, causing the individual atoms to essentially kind of wobble side to side or back and forth. And they're going to bump into the atoms next to them, and the atoms next to them and the next to them, right? The material is not flowing. An atom that's right in front of me isn't going to end up on the other side of the classroom if we had a solid piece of material. But the energy is going to go from one atom to the next atom to the next atom to the next atom to the next atom. That's the transfer of this energy wave. Okay? It's purely the energy transferring position, and it does that by slightly, very, very slightly, causing the atoms to move position within the material. But they don't move position relative to one another necessarily. Atom A is still next to atom B, is still next to atom C. They're just bumping into one another. Earlier we looked at wavelength and frequency. The other thing we have is amplitude. And so amplitude is the how much of a deflection each of those individual atoms goes through. Okay, how big of a wave do we have? How tall is it? How much deflection is there from the neutral point or the center line if you're looking, at a shear wave like this? And so it's from the center line to the top of a crest or the bottom of a trough for each one of these, for each cycle in our wave. Amplitude in sound, how we hear it, is the volume of the sound. So when I'm talking quietly, I'm producing a smaller amplitude wave. When I'm talking louder, I'm increasing the amplitude of the wave. Okay. Now my voice may also change some of the other features. The wavelength is proportional to the pitch. So this is a low wavelength voice, and this is a high wavelength voice. And I'm not a singer by any means. But that's where the wavelength comes into play. Okay? A high frequency versus a low frequency. Okay? So high frequency is higher pitched, low frequency lower pitched. High amplitude is loud, low amplitude is much quieter. Okay? And so it's a measure of the amount of energy or power that we're putting into that wave that we're putting in the part. When we did the slinky, a low amplitude shear wave was a little bit of left-right deflection. A high amplitude is if I swing it much further left to right. Okay? The frequency is how quickly I'm swinging it side to side. For the transverse wave, if I push it a little bit, that's a low amplitude wave that it sends through the slinky. If I push it much harder, that's going to cause a high amplitude wave to go through a higher energy wave. Okay? Now, ultimately, changing wavelength, changing frequency, changing amplitude is just affecting the properties of the sound in the material, but ultimately the velocity of sound in a given material is fixed at a given temperature, pressure, all that, okay? So environmental conditions can have an effect on that, but the velocity, the distance traveled per unit of time by a sound wave, as it propagates through an elastic medium, through a material, And every material, pretty much every material out there is elastic to some extent. If you have a material that deadens sound, it's less elastic. There's less, it doesn't transfer the energy. We'll get into that in a minute, what that means. If something transfers sound more easily, it's more elastic in this regard. But it is going to be given in some kind of velocity. Here it's shown meters per second, can be inches per second, can be micro inches per second, can be micrometers, millimeters per second, right? There's different, it's some kind of a velocity measurement. Miles per hour, kilometers per hour, you know. And so the biggest things that are going to do it, the material is the primary thing that's going to set the sound velocity. But things like temperature can have an effect on sound velocity. And so we have to take that into account. We have to calibrate our equipment for the environmental conditions that we are experiencing at the time of our test. And so velocity is given by frequency times wavelength. Okay? But what do we know about frequency and wavelength? They're what? They're inverse of each other. So as we increase the frequency of a given wave, the wavelength is going to go down. That's going to keep the velocity in that material constant. As we decrease the frequency, the wavelength is going to increase. Again, that's going to keep the frequency in that material constant. So ultimately, the velocity is set by the material. I'm going to skip ahead a slide before we come back to this video. Here are some examples of speed of sound. So, and what they are, this is given in meters per second. Aviation, we typically use inches per microsecond. So here you can see our atmosphere, which is primarily nitrogen with some carbon dioxide, some oxygen, right? You can see is very similar, nitrogen, oxygen, they're all similar to air, 331 meters per second. That's, I don't know, that's at 0 degrees Celsius. They also give air at 20 degrees. So you can see there's a difference of about 3 meters per second, whether it's 0 degree air or 20 degree air. Liquids, water, methyl alcohol, glycerol. Glycerol's on there, that's an important one for us. We're going to use glycerol to bond our probes to our parts. That's why they include it on this chart. It's not just some random liquid that they decided to include. We use a glycerol-based bonding agent to attach our probe to the part and limit the amount of sound that's lost between the face of the probe and the surface of the part. So then your solids, things like diamond. You can see diamond is a very, very good conductor of sound. But it would be really expensive to make something out of diamond to conduct sound, right? Maybe some kind of a lab purpose, you need sound to travel extremely fast. You could use diamond for that. Iron, steel, brass, copper, right? Aluminum's probably pretty important for us. Right? Many of the things we're going to test are aluminum. Glass is part of Pyrex glass, but then we'll be looking at, composites have plastics and other glass, fiberglass in them. So carbon, graphite is essentially carbon. Do I have carbon on here? I don't think I do. But then, like we said, the temperature can also play a role. So here is an example of the speed of sound in water. So when water is frozen, just above freezing, you can see it's 1,400 meters per second, roughly. When it gets up to about 80 degrees Celsius, that goes about 150 meters per second faster. Okay. So it can have changes. And then as it starts to get towards the steam thing, it starts to change. It slows back down. Any idea what happens to water when we get up to this point? Why does, what? Gets less dense, starts to become steam, it spreads out, the atoms spread out, so it's going to cause that velocity to go back down again. Any idea what would happen to water when it freezes? Yeah, water is one of those few things that gets less dense as it freezes, right? Ice expand. So actually this kind of makes a little bit of a U curve if you go below zero. But you don't see too much of that. Okay. So different speed of sound, we're going to have to take that into account when we're setting up our device, when we're doing testing. So we use these speed of sound examples, these charts. These give us our baseline, right? These are at gases at 0 degree, liquids at 25 degrees, solids. They don't even put a temperature here, but they do change with changes in temperature. It's very small, but we're going to be looking at inches per microsecond. So those very small amounts can make a difference. They can make a difference of 100th or 1,000th of an inch per microsecond, which doesn't seem like a lot, but it can make a difference when we're trying to measure things. So part of the setup process is we have to calibrate our device. We're going to have a test block, a standard to go against, and we have to calibrate our tester because the tester and the probe and the cable and everything are going to have different manufacturing tolerances in them. And then the temperature is going to affect not just the material we're testing, but it's going to affect the probe and the part of the probe that generates and receives the sound signal. And the different electronics inside the tester are going to be affected by temperature. And so we have to calibrate our equipment every time we use it using a standard reference. Now we would use something like, if we were going to do aluminum, we could use this velocity from the table as kind of our starting point. But then we're going to have to make some tweaks and adjustments from there. So I'm going to stop here. This is a good break point.